Hello, I'm Simon. Welcome back to the workshop. Now today I thought I'd quickly take you through the features of the Bitscope micro oscilloscope that I've got built inside my workshop cyber deck. So let's get tinkering. Now I have this running at the moment using the oscilloscope software. The oscilloscope software includes a simple tone generator, and I have a tone set to come out of one of the pins. And I've connected that pin to an oscilloscope probe, which you can see on the far left of the image. One of the B and C connectors is connected, and the signal you're seeing in the main area is the signal received on that channel through the oscilloscope probe. The small sine wave you see in the top left hand corner of the display, that's just an indication of the tone generator and what it's generating. Now you might want to generate a tone if you're, for instance, trying to fault find an analog circuit, perhaps an amplifier circuit or something, and you can switch between a number of different tones from 5 Hertz, five cycles a second, all the way up to 250,000 cycles a second. And these are just presets. You can select any frequency between these. So if I just change it and double the frequency, you'll see that the frequency here on the screen has doubled. Now, something that I noticed when doing this is that if you start going up into quite high frequencies, let's say 1 kilohertz. Now at 1 kilohertz, I need to change the time domain so that you can still see it. At 1 kilohertz, we've still got a nice sine frequency. If I go to, say, 10 kilohertz, just change the time domain again, you can see that it's starting to look a little bit raggedy. And if I carry on up, say to 100 kilohertz, and alter the time domain, you can see now that whilst it sort of resembles a sine wave, we're now starting to get some artifacts in what's being generated. It's not very clean. And if we go all the way up to its maximum of 250 kilohertz, that's 250,000 times a second, then you can see that the signal's looking quite nasty, really. It's got a lot of artifacts in it, all these little spikes and so on. It's still a sine wave as such, but it has all these little artifacts. I think that's to be expected with such a cheap device with such a large range. Let's now take this back down to something more reasonable. Let's say 1 kilohertz. Now I need to change the time domain. There we go. As well as the sine generator, you can change that to a square wave or to a triangular wave, which is quite nice. And then you can alter how that actually works, what it looks like, make it more like a sawtooth wave. And if you put it on the square wave, then this changes how much is at logic 1 and how much is at logic 0. So down here we have a few more controls. We have a control here to change if you're using a normal probe like this, or you've got it in 10 times mode. You've got the input voltage. I've currently got it set at 5.2 volts. This box here allows you to move the trace up and down. So you can move it up and down like so. Decide where you want to place it on the screen. And then this one here allows you to tell how many divisions you want. So it's the scale in effect. So if I change it, I'm currently on 500 millivolts per division. I'm now on 200 millivolts per division. So if I take that down, I can scale the signal to fit. So I have the signal generator up here set to a 1 kilohertz signal. That's something that if you added a speaker, you'd be able to hear. And this is changing at 1,000 times a second. So it's going from peak to peak 1,000 times a second. So I'm just able to see what's going on here. What I can then do is I can change the divisions to scale it up and down to get a deeper look. And I just take that down. What I can also do is I can move this up and down to get a better, to perhaps I want it further up the screen because I want to display another signal down here. So what I can now do is turn on the cursors, and this brings up this area down here in the bottom left that color codes these cursor lines with the same colors as down here. They're a bit muted. I think these would be nicer if these were brighter colors, I think. And I can then move these to measure the signal. So you can see as I move this up and down, this one here is moving. So that voltage there is 4.68 volts. If I move this there, that is 1.28 volts, giving me a total of 3.4 volts. It's 3.4 volts from there to there. So I've measured that signal. And I can do the same in the time domain. So I'll put that, say, on the peak there, and I put this on the peak there, then it'll tell me that it's a 1 kilohertz or 1.004 kilohertz signal. So you can see that if you had a signal coming in from your probe and you didn't know what it was and you wanted to measure it, then you're able to measure it using these cursors. And down in the bottom right hand corner you have some oscilloscope controls. They allow you to do things like change the bandwidth of the oscilloscope. I've got this set to 2 megahertz, but it goes all the way up to 20 megahertz. It allows you to change the number of samples that it saves from 2 kilosamples down to 12 kilosamples, so 12,000 samples. So that's what's stored in the display that you can then scroll around. It also allows you to do some things like have either sharp or smooth, so there's some smoothing. And it also allows you to change the oscilloscope from an oscilloscope only into a mixed domain scope, a spectrum analyzer, a phase analyzer, or a Vectorscope. Now, a mixed one gives you a spectrum analyzer here at the top with your oscilloscope at the bottom. A spectrum analyzer allows you to see the power of the different frequencies in the signal that's being received. This would be good for analysing a signal being received from a radio, for instance. Or if you just want to see what frequencies in a signal make up that signal. I won't go into Fourier transforms and fast Fourier analysis. This is what this is actually doing and the science behind it. But if you're interested, the Open University do great courses on physics that cover all this stuff. And these cursors then allow you to measure a bandwidth. So if you wanted to measure the width of the signal here, you could do that, and it shows you that width here. Look at the others, the spectrum analyzer, it just gives you just the spectrum analyzer. So here I'm using the signal generator to produce a 100 Hertz sinusoidal wave. That's the top wave, and then I've created a little capacitor and resistor circuit, and that's being measured on the green line at the bottom, which is the second channel of the oscilloscope. Now that should result in the two signals being slightly out of phase as the capacitor charges and discharges. And if I just move this one up, you can see that they no longer line up. one is out of phase with the other. What you can also do is you can plot this signal against this signal. So if you imagine at the moment we have time in this direction and then signal up and down, but if I was to plot the signal strength of channel A, the yellow line, in one direction and channel B in the other direction, that's what a Vectorscope does, and what you end up with is a little circle. So this is now plotting those two signals one against the other, and I can sort of move this around a little bit so I can get a better display, or I can change the scale if I want to look at something in a bit more detail. I can do that. So that's what the Vectorscope does. I don't really have a great deal of use for it. It can be quite useful for diagnosing problems with TV displays that are using the old PAL or NTSC signals. Not something I'm ever going to be doing, but it's also the root of how those original vector graphics arcade games worked back in the 70s and early 80s. So here's an example of using the signal generator. I'm producing a 1 kilohertz signal, and you can see with the probe connected to that signal, it coming up on the oscilloscope. Now, in circuit with this, I'm going to now add a speaker, and you'll see what happens to the signal. And you can hear the speaker as well. Now I'll just adjust the scale, and you can see that the speaker is introducing some noise into the overall circuit. So you can see the impact that the speaker is having on the signal that we were putting in. I can change the tone, so move it to 500 Hertz maybe. It's very quiet because there's no amplifier. The oscilloscope's driving the speaker directly. I now change and if I change it from a tone to a square wave, you can hear the additional frequencies. And if I now change the oscilloscope to a mixed domain scope, you can see that to make that square wave up, you need all of these frequencies with diminishing powers. If I now just swap it back to the sine wave, you can see that most of those frequencies have now disappeared, and they're all, the frequency is actually dominating is the frequency that we've set it to. If we change that frequency up, you can see it's moving to the right as it gets higher and higher in frequency. We now can't hear it. I can keep moving it to the right, and you can see that this main peak here is moving to the right. So I still have a lot to learn about this tool, but hopefully you can see the utility of it for a tinkerer in their workshop, fixing things, tracing signals through circuit boards and so on, trying to find why the thing that you've made hasn't quite worked. If you've got any questions, then please leave them in the comments. If you've enjoyed this video, please leave a thumbs up. If you'd like to see more videos like this, then please subscribe. And if you want to know how I built this, then have a look over there, because there'll be a video that shows exactly how I did it. Thanks for watching.